Section 5.4, in the second part of the section, we're going to be looking at altitudes of triangles, which is the last special segment we're going to look at in triangles. Now, what is an altitude? An altitude of a triangle is a segment that goes from the vertex perpendicular to the opposite side. Remember that perpendicular means it has to go at a right angle. So it's a segment that goes from a vertex at a right angle to the opposite side. And I made a note here that you might have to extend the sides for this to work. And I'm going to jot a note down, remember perpendicular at a right angle to the opposite side. So let's see if I can create my first altitude here. So if I go from this vertex, I have to go at a right angle to the opposite side, which here means I just drop it down. And if I mark it as such, there you go, you have an altitude. Now you might be thinking this has a different term. A lot of times when we're talking about finding like area of triangles, you're looking at the height of a triangle being from the vertex at a right angle to the opposite side. It is also a height of the triangle, and altitude is the same as a height of that triangle goes from a vertex to the opposite side. And I made that note that you might have to extend the sides, because if I look at, let's say I look at going from this vertex here to the opposite side, you can tell this is not meeting at a right angle with this side, and if I go this way, it's worse and worse. It's becoming not even close to a right angle. And it looks like it's getting closer and closer to a right angle here, but even there, it's still not a right angle. What I'm going to have to do is extend the side out here and then try to find where that would meet. So let's do that. I'm going to take this line, kind of dotted line, and I'll just extend this side out further. And now I can grab this segment tool and go from this vertex. And now I just want to meet at a right angle to that side. I'll pick as close to a right angle as I can visually find. How about there? So this would be another example of an altitude, but you notice I had to extend that side to actually meet at a right angle with it. The same would be true here. If I want to do an altitude, I would have to extend this side further out this way because going here would not meet at a right angle. Let's go into Geometry Sketchpad and do these altitudes. Actually, I'm going to start from scratch here and make a triangle. I'm going to take this segment tool and create my triangle. As long as you see that circle comes around that point, you know you've matched them up. Alright, and now to make altitudes, what you need to do is click this point, and I want to go at a right angle or perpendicular to this side. So I highlight those both, and I say construct a perpendicular line. So there we have an altitude. Let's change that color maybe to red. How about from this point to this opposite side? So I highlight both, and I again construct a perpendicular line. There's my next altitude. And finally, from vertex C to the opposite side, I need to do a perpendicular line. Hey, look at that. You notice that these points are all coinciding here. All the altitudes meet at a point of concurrency. I can make that point go further outside the triangle. I can change the position of that point and bring it inside the triangle as well. And am I changing all these? You still notice these red lines are my altitudes. They meet at a right angle. But you're noticing that point, the point of concurrency here, can be outside the triangle. And we'll talk about that some more. So you're probably wondering, what is this point of concurrency called where these altitudes meet? It is called the orthocenter. Alright, so once again, we have these special segments being concurrent. Concurrency of altitudes of a triangle. They intersect at the orthocenter. And I have noticed the location of the orthocenter in the Geometry Sketchpad you guys just saw. That orthocenter can be located in the triangle, on the triangle outside. So if I do an example quick in this acute triangle, again I'm going from a vertex, trying to make a right angle with the opposite side. And even just in my quick approximation, you notice in an acute triangle, the orthocenter is located inside that triangle. Again, all of these I was approximating visually as a right angle to the opposite side. In a right triangle, something kind of interesting happens. If I go at a right angle to the opposite side from this vertex, I'm on the leg. If I go from this vertex at a right angle to the opposite side, I'm just going over that leg as well. And if I go from this vertex right angle to the opposite side, you notice I'm actually meeting on the triangle right on the right angle. On the triangle at the right angle vertex. And finally, in an obtuse triangle, remember that this will involve me extending the sides. The only altitude that I can do from a vertex to the opposite side without extending would be right here. Go at a right angle to the opposite side. But that's it. Because now, once I would try to go from this vertex to the opposite side, this would not be a right angle anywhere here, but if I extend it out, and I know it's going to be perfectly vertical in this case, because if I extended this side, it would have been perfectly horizontal. And I know this is an altitude because it does meet at a right angle here. I'm going to extend my previous altitude so that they actually meet somewhere. And I guess I have one more to do, and I'm probably going to have to extend a side again. If I want to go from this vertex to this opposite side at a right angle, I'm going to have to extend this side as well. Now let's go from this vertex at a right angle that side. That looks pretty good. I extend it, and notice they are all crossing at the orthocenter in an obtuse triangle. That location, the orthocenter, is outside the triangle. Way outside in this case, because of that obtuse angle. So the orthocenter can be located anywhere in a triangle. No special properties other than the fact that it can be located anywhere relative to the triangle. We're going to talk about a few things related to isosceles triangles here and some of these points of concurrency. So when you have an isosceles triangle, something cool happens. The perpendicular bisector, the angle bisector, the median, and the altitude are all the exact same segment from one of these angles in an isosceles triangle. Remember, in an isosceles triangle, we have the two congruent sides called legs. We have our base. And when we talk about the angles, we have two base angles off of that base. The angle between the two congruent sides is your vertex angle. And if I draw this one segment here from the vertex to the opposite side, now if I go at a right angle, that's what we've talked about today. This is now an altitude. Check. If I go to the midpoint of this opposite side, if this is from the vertex to midpoint of the opposite side, and it would be midpoint if these two are congruent, now it's a median, right, to the midpoint of the opposite side from the vertex. The fact that it's at a right angle and going to the midpoint, it is now a perpendicular bisector of this side because it meets at a right angle, perpendicular, and it cuts it in half, bisector. This is also an angle bisector, and these two angles are congruent. So check off on all four of these. Now, which angle are we going from with this segment? This is from the vertex angle of an isosceles triangle. You have that one segment being really all four special segments at once. So kind of cool thing about an isosceles triangle here. A few more interesting things that happen with all of these points of concurrency. First of all, you have the Euler line. There are 3 points of concurrency that are collinear. Remember, collinear together on a line. They're on the same line. The orthocenter, the centroid, and the circumcenter are all on this Euler line. Or Euler line, I should say. And I'm going to see that in Geometer's Sketchpad here. There's 3 that are on the line, 1 that is not. And I just did every single point of concurrency in this triangle, and you can notice I can move these around here and change the triangle. And I can put the orthocenter and circumcenter outside of that triangle in an obtuse triangle, of course. But I'm going to see that 3 of these points are always on the same line, so I'm going to grab my line tool and make it an extended line. And I'm going to start at the orthocenter. And if you notice, if I go through the centroid, this also goes through the circumcenter. I'm going to make this a thicker line here. I'll make it black. Oops, I don't want that line there. Sorry. But if you notice, look, I'm going through the orthocenter, centroid, and circumcenter. I'm not going through the incenter. If I move this triangle around, I'm still going through orthocenter, centroid, and circumcenter. No matter what. Incenter, again, is not on that line, but the other 3 always are. I can bring the orthocenter and circumcenter outside, still going through the centroid. Incenter is the only one that is not on that line, always. It's kind of neat. The Euler line there has 3 of those points. It's just not the incenter on that line. And one more thing, all of the points of concurrency meet at the exact same location. All the points of concurrency come together in what kind of triangle? Maybe I'll go back to my Geometry Sketchpad sketch here and see if I can make all of these points go to the same place. It's getting closer. Look at that. Every single line ends up being the perpendicular bisector, the angle bisector, the median, and the altitude. Well, didn't we just see that that happens when you have an isosceles triangle? Well, that means that from this line, then, these two sides are congruent. And from this line, these two sides are congruent. And from this line, these two sides are congruent. Because an isosceles triangle, when it goes from the vertex angle, those lines are all the same. Well, wait, if all of the sides are congruent, what kind of triangle do we have? We have an equilateral, equiangular triangle. And in that specific kind of triangle, in a regular triangle, equilateral or equiangular, all the points of concurrency come to the exact same location, the very center of that triangle, which is kind of neat. And we're going to end with a proof here. Prove that if an angle bisector is also an altitude, then the triangle is isosceles. I'm going to put a little triangle in here. Prove that if an angle bisector is also an altitude, then the triangle is isosceles. I'm going to draw that line because it's supposed to be an angle bisector and an altitude. Let's label the vertices here. This could be triangle ABC, how about? And I'm going to do a paragraph proof, but I'm going to do it a little less formal. I'm not going to do like every statement and reason, but I will explain myself here. Oh, I better put like point D here so I can talk about this segment. Okay. So I'm starting out with this blue segment being an angle bisector and an altitude. So I'm going to start that out saying AD is an angle bisector and an altitude. You know what? I'm just going to say is an angle bisector. I'm going to start with the first part there. Angle bisector. AD is an angle bisector, so what do you know? Well, if this is an angle bisector, it bisects the angle here, and so we have two congruent angles, right? So I'll name those angles. Angle BAD is congruent to angle CAD, the ones I just marked, by definition of angle bisector. Alright, what about the fact that it's an altitude? AD is also an altitude. And what does it mean to be an altitude? It goes from the vertex at a right angle to the opposite side. Well, wouldn't that mean that these are both right angles? And we know that right angles are congruent. So angle BDA and angle CDA are right angles by definition of altitude. Actually, I should say that AD is perpendicular to BC by definition of altitude, and then these angles are right angles by definition perpendicular. And so they are right angles, and they are congruent. We know that right angles are congruent. So I'm skipping steps here because really I'd have to say that these lines are perpendicular by definition of altitude. These are right angles by definition of perpendicular. These right angles are congruent by right angles congruence theorem. I'm listing the congruent, they're the two right angles and saying they're congruent. Look at this, we got two angles congruent here. We got the right angles congruent here. Well, if I'm trying to show that the triangle is isosceles, if I could prove these two smaller triangles congruent, then I could use CP/CTC to say that corresponding parts are congruent, so that these sides would be congruent, and that is the definition of isosceles, that it has two congruent sides. So how can I prove these two triangles are congruent? Well, I have these angles, I have the right angles. Don't they share this side right here? So side AD is congruent to itself. That line segment is congruent to itself by reflexive property. I guess this is the only one I'm really explicitly stating the reason for. So I can list the congruent triangles. I can say triangle BAD is congruent to triangle, and I gotta name the other one correctly. If I do BAD, I should do CAD. By what reason? Well, we have angle, side, angle, right angle, side angle, by angle, side angle. Then, remember I'm trying to show this triangle is isosceles, so I have to show that these two sides are congruent. And I do know that side BA now would be congruent to side CA by CPCTC because we have congruent triangles here, so corresponding parts of those congruent triangles are congruent. And if you have two congruent sides, you know a triangle is isosceles by definition. So now that original triangle ABC is isosceles by definition. So I had to use the definition of an angle bisector, that we have two congruent angles, of altitude, that we make a right angle, or we meet at a perpendicular with the opposite side, making congruent angles. We had a shared side. Now these two smaller triangles were congruent. Then I can use CPCTC to say I have two congruent sides, which means this triangle is isosceles. Alright, so talking about altitudes today, and a little bit of a summary of all of the special segments we've done in triangles.